In this video, we will see what happens to Fermi level with applied electric field. So we have seen Fermi level in different materials, that is intrinsic N-type and P-type. Now we will see what happens to Fermi level or energy band in a material with an applied electric field across it. So we will try to explain drift current in terms of the energy band diagram also in an applied electric field. So after that, we will see what happens to equilibrium Fermi level when materials are in contact and there is no current between them. Let's start with Fermi level with applied electric field. So let's say we have a semiconductor bar. For this discussion, it doesn't matter whether it's intrinsic N-type or P-type, but let's assume that it is an intrinsic material and the energy band diagram will look something like this. So for simplicity, let's assume that this is our positive X direction. Now this is without any applied electric field. So we have our conduction band, the Fermi level and the valence band. Now let's say we apply an electric field across this material. That means let's say we apply an voltage and it will set up an electric field from the positive end to negative end. So we can draw the electric field like this. So we have an electric field across the semiconductor bar. Now we want to see what happens in the energy band diagram. Now when we apply an electric field across the material, the electrons will tend to move from negative terminal to positive terminal and holes will move in the opposite direction, that is from positive terminal to negative terminal. So that means the electron energies should be higher at this end and should be lower at the other end. Let's see how it is. We have a slope in the energy band diagram, or we have EC, here we have EF and here we have EV, that is the conduction band, Fermi level and the valence band. Now we can say that there is a gradient in the electron energies. That means the electron energy is high at this end compared to the other end. Now we will be looking at a way to find a relationship between the applied electric field and the electron energies. And one more important point to note here is that there is no change in the energy gap from this end to this end. That will always remain same. That is because we are not changing the properties, but we are simply adding energy to the system. So now let's find a relationship between these two. Now the best way to do it is to use the electrostatic potential as an intermediary. So we know the relationship, that is the electric field is the negative gradient of electrostatic potential. Now if we can find the relationship between V of X, that is the electrostatic potential and electron energy, we are done. So we know that relationship, that is V of X will be equal to the electron energy divided by minus Q. You may wonder why this negative sign. It's because we are dealing with electron energies and the electrostatic potential is always defined in terms of positive charges. So there is a negative sign. Now if we substitute for V of X in this equation, that is substituting 2 in equation 1, we will get E of X equal to, the electric field equal to, the negative sign here and the negative sign here will get cancelled and we will have 1 by Q dE by dx. The conclusion here is that when we apply an electric field, there will be a gradient in the electron potential energy. That is this slope here. And we can visualize the charge flow in the energy band diagram as well. Now we know that these carriers tend to move from higher potential energy to lower potential energy. So the electrons tend to move in this direction. That is visible here also. So the electrons will be tending to move in this direction. And what about holes? So holes will move up the band. That is because we have drawn electron energies here, not the energy of positive particles. So it will move uphill. So the electrons, always remember, will roll downhill. That is easy to remember. And holes will go uphill. So the hole will tend to move uphill. So this is really important if you want to visualize the drift current in terms of the energy band diagram or Fermi level. If there is a gradient in the Fermi level, we can say that there is some current associated with it. Now we will see about Fermi level when two materials are in contact.